Okay. The class today we have chapter thermochemistry chapter. In thermochemistry, okay, let's get started over. It's gonna be calorimetry, right? In calorimetry, we talked about some basic fundamental chemistry that we talked in previous classes. First thing we need in this calorimetry, we need to know what is enthalpy. Because calorimetry is all about how to calculate enthalpy. It is a calorimeter. We use this fancy stuff to calculate heat of a reaction. So what is enthalpy then? Heat of a reaction. Exactly. So how you calculate the heat of the reaction? If you remember, enthalpy equal to the Q, and Q equal to mass of a reactants or substance that you put it in this cup, and then C, lowercase c, small letter c, and then delta T, right? You remember that? Yes. So we can calculate using this calorimeter to calculate enthalpy. So what is it actually? It is a like styrofoam cup. You remember, if you buy a coffee, they give you styrofoam cup, right? What is styrofoam, cup for? Because if you take a very hot coffee, you can hold it by your hand, right? Because heat is not transferring to out. So your hand able to hold it, you don't even feel hot because heat is not transferring from inside, from styrofoam. And heat is not going in either. That means the heat you're calculating, that is exactly how much it's producing or how much it is absorbing. That heat change, that temperature change, you can get exact amount of heat you have in there. So we'll be doing a lab for this styrofoam calorimeter and the next weeks. So before going to the math of this calorimeter, I like to go a little bit refreshing your memory with a specific heat capacity. 3 types of heat capacity we talked, right? This one is specific heat capacity. So specific heat capacity, what is it? 1 gram, yes. One thing good, 1 gram. 1 gram of substance, okay. Tell me complete definition. Heat capacity, right? How much heat it can attain. The amount of heat you need to raise temperature 1 degree for 1 gram of a substance. That's called specific heat capacity. So for the specific capacity, the unit would be, so as I said, 1 gram of substance. And you, so the amount of heat you need, heat is energy. Energy unit is joule, right? Joule, amount of heat you need to raise temperature 1 degree, so degree centigrade, and per gram. For 1 gram of substance, 1 degree centigrade amount of heat you need. That's called specific heat capacity. That's the unit of for that, which is C. And specific capacity, we said that would be varies depending on the material. If a compound gets hot earlier, quickly, like for instance, if you have a piece of metal of iron, like iron, and if a piece of iron, if you have a water, which one will be heated up quickly? Which one will be which one will be heated up quickly? Iron will be heated very quickly. It's going to rise temperature few hundred very quickly. But water takes few minutes to raise temperature about 100 to boil, right? That means which one has high heat capacity?
Water.
Water. Because it takes time, it absorbs a lot of heat to raise. So it has higher capacity. So then iron, you see, this is the water, you have 4.18, and iron you have 0.994, 2 different heat capacity. And that's what you need for C, to calculate amount of heat in the system. right? This is different types of calorimeter. It's called bomb calorimeter. How it sounds? Bomb calorimeter? Bomb, right? Is it made of bomb? No, it's not. But why said that? It says because it's something insulated. But I don't know why it says that. But why? What you can see, something is like insulated. It could be bomb if it is not taken care of. So as I said, this is like sophisticated way of measuring enthalpy. It's like a calorimeter. But what it has two chambers. One inside chamber, one outside chamber. The inside chamber is made of metal, usually steel, and outside chamber is made of concrete. And this inside chamber has your reaction going on. And the amount of heat is producing that will transfer to outside, which is full of water. And you see the fan is moving to circulate water around. So the amount of heat transferring from inside to water, that you can see by thermometer. So if you know how much water you're taking, the mass, and specific heat capacity for water, you know that, and for temperature from thermometer, final minus initial delta T, then you can calculate how much heat producing or how much is needed absorbing. You can calculate this calorimeter. And this is kind of similar to nuclear chamber. Have you have chance to see or visit nuclear chamber ever? Or have you seen the YouTube or video? No. So nuclear chamber is like similar, exactly similar mechanism. Nuclear reaction is going on inside. It surrounded the water, continuously circulating to cool that down. And if by any case water does not circulate, then it's going to be extremely hot. It's going to melt the metal because of a few hundred, even thousands degrees centigrade. Then this metal will melt. You know that nuclear have a lot of explosion in previous history, right? Russia has a big explosion. You know, the Chernobyl atomic plant has a big explosion. So by any case, it doesn't work properly, or it doesn't cool down, it's going to explode, or it's going to melt the inside. That's also going to be worse. Anyway, so let's go back how to calculate enthalpy from this calorimeter. The equation we have, you can see from the screen, mass times specific heat capacity times delta T. And you know all of them. So we'll be using that to calculate amount of heat. First of all, okay, before going to the exact calculation, I would like to have just some practical problem you solve. That would be easier for you to understand or to solve more critical problems. Do any of you have swimming pool in your home? Anybody have swimming pool in backyard? Okay. You do. Okay, Imad, you do. Okay. Both of you have swimming pool. For instance, do you take shower there every day? Not very often.
The swimming pool?
Do you take shower in the pool sometimes?
Never in my life.
Swimming pool? Of course you do sometimes.
Sometimes.
Sometimes, right? Suppose nowadays, like temperature at the night time is like about 70 or 60, right? Pull it a little bit down, right? So if it is like 60 at night or 70, suppose, then you want to take shower before you go to sleep, right? So then you plan to take shower, you want to warm up first, then go take shower, right? So let's see your so Imad, your swimming pool, like for instance 100 kilogram water you have. You want to raise temperature for 10 degree, right? For 10 degree, 100 kilogram water. So can you calculate how much heat you need how much enthalpy you need to raise temperature 10 degree, which is 70 to 80 pretty good warm to a shower. And please calculate how much enthalpy you need to raise temperature 10 degree for yacht's swimming pool. Do that. First of all, 100 kilogram, right? 100 kilogram is water, that's medium size, right? Not too big. And then go specific heat capacity, which is exactly 4.9.
188.
Yeah, 4.18. Yeah, 18 joule per gram degree centigrade times and delta T. How much you changing? 10 degree. So it will be 10 degree centigrade Celsius. So Celsius cancel out, and then gram is not cancel out. What you can do? You can make it to gram. So instead of writing 100 kilogram, you write 10 to 4 kilogram.
I thought you had to convert it to grams.
I need convert it to kilogram. So 10 to 4 gram. Then you cancel out gram and gram, right? So how much enthalpy you need to raise temperature 10 degree?
4,180.
4,000. Can you make it scientific notation? And write sig figure, please.
I think 4.18 times 10 to the 6.
Exactly. 4.18 times 10 to 6 joule. How can you do that? Look at that. 4.18 is going to be same as it is, and it will be 3 sig figure because that's the highest sig figure you have, right? And then how many? What is the 10 to negative 4 in here, 5 in here, and 6 in here, right? And then 10 to negative 6, 10 to 6 joule. You don't need calculator even. So, any question you guys have for this problem?
So you calculated,
Yes. You can calculate your swimming pool, how much heat you need to raise temperature for 10 degree.
okay.
Got it? So you can warm it up?
Yeah.
Okay. Then second one is here. Solve it 2. If you have 2 kilogram of piece of iron, so you have a mass, then temperature 0 degree to 557 degree centigrade, right? It gets hot extremely. There are some people, right? It gets hot very quickly. We don't want to do that, right? Anyway, so temperature delta T, mass you have, and for iron, what is the specific heat capacity?
0.449.
Yes, 0.449. So do that. So if you do that, even though it's very easy, please do that. Remember we talked about that. Whenever you take something very easy, sometimes you do more mistake, which I saw in copper gas. Question is 2 gram of iron you're heating and raising temperature 0 degree to 557 degrees centigrade. What is the enthalpy, or how much heat you need, or how much heat is producing? Right? Question could be either way, right? So question could be how much heat is producing by this piece of iron. Or question could be how much heat is being evolved with this heating. Both is same. Got it? Okay, can you do that? Okay, let me see.
Yeah, well, actually,
This-
But what about the pH changes? Do that?
If it's salt water, it's not.
I'm trying to make something organic, so no salt water, no chlorine, really healthy one. My method is small, organic, I mean, I'm still using the word organic. I mean, no salt water, no chlorine. I don't want to say like
You can use rock, you can use rock to do it organic. Yeah, because it's still kind of water naturally.
All three of those things.
something like that. I'm just gonna grow.
Huh?
Yeah, algae will grow.
You just do
I'll take gonna grow.
So I wouldn't treat your water all the time.
I'm not making like portable small one, so I can change it as you.
Are you gonna swim in there? Or?
Just take shower.
They're pretty live here.
Yeah.
It's pretty cool.
Yeah. So let me see. I'm just cooking something like that. I'm just cooking. Okay, 2000 grams, which is 2 kilograms, right? And the specific capacity times the delta T, the change of temperature. Is it right stick figure? Yes. Is it right stick figure? Yes or no?
Yes, because it's 2.0.
So there is 3 stick figure, and 1 stick figure.
Don't we go off of that problem?
Yes.
So
Or 2 stick figure, that's good. 2 stick figure, yes. Based on this problem is 2 stick figure. Yes, sir.
Why don't we use the 500 kilojoule?
500 kilojoule, you could do that. Same thing. This is actually 500 kilojoule. This is the answer. Answer is given there. Just playing it. Oh, you didn't trust the answer? You didn't trust it? Okay. And then we can go to the, let's see, different way of problem, but kind of similar. I mean different, I mean that you see the copper is warming up from -8 to 37, right? And then mass is given. The question is, how much heat absorbed by this copper penny?
Just the capacity.
Same thing, same formula.
Chart.
Copper is,
0.385.
yes. Okay.
Do we need to know all this for the test?
Remember I said you guys should have trust on me, right?
Okay.
Yes. Okay, who can solve it quickly?
It's easy.
Let's see if you know what you're doing.
The engineer.
There is easy one. Easy one is not always easy actually. So easy part is not easy, guys. Remember, without practice, if you practice, that's gonna be easy. Until that, it is hard. Easy part, you don't practice. You take it very easy. Make it done. That is the easy. So I don't know why I'm making this question. What is the reason behind it, you know? Look at them, -8, that will be confused with that, you know? There will be a problem, trust me.
You have to subtract it.
Heat capacity? Heat capacity is point for the copper, right?
0.994.
He's right.
No.
What
is it?
0.385.
0.385.
385.
Yeah.
Yes.
It is.
And the mass of, you got velocity, you got C, and the mass is
Oh, I
8.1 gram.
I didn't either.
So let's see.
I thought it was just like a dash. Just there. Okay, that makes sense.
Okay, anybody can correct him, we'll get the same point. Remember that. Anybody can correct him.
What does that say, 45?
If he is wrong,
It should be final minus initial, isn't it?
Yeah, that's
What he did, it's a -8.
No, that's negative 8.
Yes, he played very strong, very
Boy.
good tricks. Yeah, good job.
Oh,
That's a negative eight.
detached.
I thought that was.
I thought it was just an 8.
Yeah.
That's not full.
Yeah.
Dang.
So am I wrong?
No, you're right.
know what? Everybody's saying he's right. How he's right? Based on positive weight.
Based on that, yeah.
Exactly. So that's how I
We
wanted to
should get a
make.
point. That's funny.
That's
37.
Anyone has a couple?
And go back.
53.7.
Well, those are two together.
53.71.
Yeah, 37 plus anything.
Okay. Okay, last one. Last problem for this formula. You have an aluminum block which is 27.5 degrees centigrade. It absorbs 725 joule of heat, and this is called enthalpy, right? Okay. So you have a mass, you have a degree initial temperature, Ti. What is the final temperature? Can you solve it?
She got it.
That's what the initial heat.
I need a print.
I was trying to bring down my
Is there one on the top?
I think it's on that paper right now.
Oh, you just doing the exam. Okay. Yeah, there. Good partner. Fifty-five times. Specific heat capacity is.
The wind.
55.
No. I showed one.
Let me see what I get. Kind of work it back.
Is it? We have 27.5, so like minus temperature minus 27.
Yes, yes.
Because it says
She'll do it. She's gonna do it later. I saw.
So it's 17. You gotta work back.
I'm actually very bad when I have to, I have to take your exam. My unit is, what I said, my unit is on the block call. You don't know, you forgot about that. I understood that.
Yeah,
That's not problem.
I can show you.
Or you forgot about the rules?
I can show you. After that, I can show you why.
You're still going to
Oh, next time I'm gonna see that. I'm just gonna be.
You're trying to find the change in temperature. Yeah. That's the issue. To 27.5 Celsius. So you don't know the change in temperature that you have heat. You have the mass.
Okay, then delta T. So delta T equal to, so TF minus TI, right? And then, so
Yeah, the 14.6 must be on the other side.
So T, we need TF, right? TF equal to delta T plus T1, right? So this is,
It just has to be switched. The 14.6 is supposed to be on the other side.
okay,
So it's basically the same.
let's do the same.
Yeah.
The same. So what will be the 40, yeah, 40. The same. So delta T is 16 point, so this is here, and Q1 is, yes. Wonderful. Then let's go to the next idea. The next type of problem is, for instance, You have this water, right? In this water, you not drink like hot water. Remember, I taught you guys why you have to drink hot water. Do you guys still drinking cold water, guys? Unfortunately, yes, right? That's also okay, but not cold. Cold is not okay. That's stopping your mechanism, stopping your digestion. You know? You guys now young, like 20s, right? Everybody 20s, yes. No, I almost everybody. You're gonna feel after 10 years. You don't wanna feel 10 years. Enjoy your time eating cold water. You'll see that. Please stop it. You know, right there. You need to drink at least room temperature. Okay. Okay. So somebody really following my rules. Okay. Somebody really following healthy rules. Healthy rules is make a warm water, right? So you might think, okay, how can I make warm water because I got already room temperature water, right? You got it from the filter machine, right? So you got water in here, and then you took some microbial hot water, and you mix it up, at least making it a bit warmer, right? So one is cold water, one is hot water you made. You know, combined together, make it a little bit warmer, right? So think about that. Two things in here. One is cold, other one is hot. You mixing together, and finally, the cold one will be absorbing heat from the hot one. So do you think amount of heat absorbed by cold water is going to be equal to amount of heat released from the hot water? Is it going to be same?
Yeah.
Have to be same because amount of heat releasing by hot water taken by cold water. So they are same. So my point is, if two object is two different temperature, mixing together, the amount of heat is absorbing equal to the amount of heat is releasing. Right? It could be one metal, one liquid, could be two liquids, could be have to be at least one liquid to make it homogeneous temperature. So how that would be? Let's see. Different example. In that case, how that would go? It should be like that. Yes. There you go. Now you can see. So two objects could be one metal, one water. Could be both water. Let's say one is metal. So the metal heat equal to enthalpy of metal equal to mass times specific heat capacity of that metal, and the temperature it started off and then temperature is final. Same water mass, specific heat capacity of water, and the temperature difference between final to initial. So one thing you notice here, first if you do not look at the enthalpy point of view, you might think how it is possible plus equal to minus, right? It is equal because in enthalpy point of view, one releasing, one absorbing. So if that happened in any scenario, in any problem, can you solve it? Yes, you can, right? By using this formula. Let's see a problem. You have a cube of aluminum. You initially it was a little bit higher temperature, 45.8. That is mixed with it, submerged into the water, which is 15.4 degree. And then finally, both become in equilibrium. And they mixed up and they become a final temperature. Final temperature is going to be same for both or two different?
Same for both.
It's going to be same, yes. They finally meet in a middle temperature. So I have sometimes I make some multiple choice question for exam, like, okay, for instance, you're mixing 0 degree water with 100 degree water. Is it the final temperature will be 50? It is going to be 50 if you same amount of and both are same substance. If they are both substances same, both are water, amount is same, then the middle temperature is going to be middle, like 50. One is 0 degree, one is 100 degree. If both are water, middle temperature will be 50 degree if both are same amount. But what if same mass of water, I have same mass of aluminum, aluminum cube. That will not be, it's not going to be 0, 100, it will not come to 50. Because it depending on the specific heat capacity of both. And specific heat capacity is not going to be same water and aluminum cube, right? So let's solve this one. You have a cube of aluminum initial this temperature, right? Solve it. Let's see what you have. Let's solve together. So the formula is Q of metal equal to Q of water, right? I can do H2O, I can do W. Okay. So it is going to be negative. Now question is, can I put negative in this side? Is it possible? Sure, no problem. It is same actually, right? So this is a big question. Not, if I don't talk about it, that might come to your mind. Hey, which is endothermic, which is exothermic, which is releasing, which is absorbing. It doesn't matter. You do have to look at that. Look at my previous one. Look at it here. The metal was the heart, right? Technically that should be negative. That's the one releasing, right? But I did other way. Why? To show that it does not matter. Because here is not, that's what our goal is. Goal is, since it's materially same value, we can stay away from this confusion, okay? And again, you can do it that way. Okay, let's go left side. And then, left side is metal. Metal, so mass of metal, and then specific capacity of metal, and T final minus T1 of T of aluminum. Look at that. I did not put Ti here because T of aluminum is the Ti. Right? And then mass of water is 105.3 gram. And specific capacity, so let's go mass of water times specific capacity of water times TF minus T of water. Look at it here. TF is same in both cases, right? Because finally they will come to one temperature.
We forgot the negative.
What is that?
We forgot the negative side.
Oh, negative sign, yes. And then let's put the values. So cube is 32.5 gram, and for the aluminum, specific heat capacity is 0.9.